So last time we talked about the composite and combination of functions. Now we're going to move into our inverse functions, which have a very close relationship with the composition of functions that we're going to see a little bit more towards the end. And this also plays very heavily into our upcoming sections on exponential and logarithmic functions, which are inverse functions of each other. They have a very close relationship. One of the first things we need to talk about, though, is what we call a one-to-one function relationship. Recall that when we have a function, or whether or not to define whether or not we have a function, is that every corresponding x value of an equation or a relationship can only correspond with one y value. So if I pick any point on this line, we can see that every x value, the horizontal part, only has one y value that matches. Even when we talk about a quadratic, which has this U shape, and I can see that every x value corresponds with only one y value, even though this y value happens to show up more than once. That's okay to have a function. Now, when we move into a one-to-one function, this relationship is not okay anymore, because this doesn't allow us for the inverse, which we're going to come up with in just a moment, to also be a function. And so we're looking for this one-to-one relationship where each x value corresponds to only one y value, and the other way around has to be true as well. Each y value corresponds with only one x value. So what we're looking for here is basically no duplication. All right, no x values duplicate and no y values duplicate. So when we look at our first function here, and we have function r, we have x values of 1, 3, 5, and 6. So since we have x values of 1, 3, 5, and 6, there's no duplicate. So far, we're good. We don't have an issue. But now we also need to check the y values. And you check the y values, and we have 2, 4, 6, and 7. 2, 4, 6, and 7. And again, in that list, there's also no duplication. Okay, so we want to make sure that in each list of x values and y values, nothing's being duplicated. Let's look at function g. The x values for function g are 0, 3, 6, and negative 2. 0, 3, 6, negative 2. And none of those numbers show up more than once. If we look at the y values, we have 3, 7, 7, and negative 2. 3, 7, 7, and negative 2. Well, because the 7s show up more than once, that's not a one-to-one function. It's still a function because the x values don't repeat, but it's not a one-to-one function. So here we have a one-to-one function, and this is not a one-to-one function. Now, another way that we can look at whether or not we have a one-to-one function is through what we call the horizontal line test. Now, this varies from the vertical line test that we learned much earlier. The vertical line test tells us whether or not we have a function, if a relationship is a function or not. The horizontal line test tells us whether or not it is going to be a one-to-one function. So if it passes the vertical line test, it's a function. And if it also passes the horizontal line test, then it's a one-to-one function. And so in order to pass the horizontal line test, it cannot intersect the graph at more than one point at a time as we move that horizontal line up and down. So when we look at some graphs, we can identify whether or not we have one-to-one functions by doing a horizontal line test. So real quick, I'm just going to do the vertical line test again just to show that these are indeed functions, because no matter where we draw a vertical line, it's always going to intercept no more than one time on the function. However, now we want to move into the horizontal line test. And you can see that if I draw a line straight across, well, here I'm intersecting my graph multiple times. The only time that I don't intersect it more than once is at the vertex. So this is not a one-to-one function, not one 1. Not 1 to 1. But here, if I draw a horizontal line, I can draw it anywhere and everywhere I want. And I don't have any points intersected more than once, so I do have a 1 to 1 function. Now, what does all this matter, okay? Whether we have a 1 to 1 function or not. Well, if we have a 1 to 1 function, what we can do then is we can identify whether or not we have an inverse function or an inverse relation that is still a function when we find the inverse. And what the inverse is we are switching the coordinates of the ordered pairs. We take the x values, we take the y values for every ordered pair, and we switch them. And if we have a 1 to 1 relationship, when we make that switch, then we still have a function. Now, we have special notation for inverse function. We see this notation here as f kind of to the power of -1, but we read that as f inverse. In some places, you'll just see it with the negative sign. You won't see the 1. It's just a slightly different notation, but it represents the same thing. We're talking about the inverse of the function, where we switch the x's and the y's. So when we have a 1 to 1 function consisting of all of our ordered pairs x and y, the inverse function will have the ordered pairs of y comma x. We're going to switch those ordered pairs to create new ones, and then what was the y values become the x values, and what was the x values become the y values. So we'll start really easily and we'll just look at these ordered pairs. So when we're trying to find our inverse, this was our function that is 1 to 1. To find the inverse, we just take all the x values and all the y values and we switch their places to get our new ordered pairs. So instead of having the point 3, 4, I'm going to switch to 4, 3. Instead of having 6, 2, I'm going to switch it to 2, 6. Instead of having -3, 2, I'm sorry, or 2, -3, it becomes -3, 2. And instead of having 4, -5, it switches to become -5, 4. And so that allows us to identify what the inverse function is by switching all of the x and y values to create new ordered pairs. Now, if we have an equation or a function written out as an equation and we want to identify the inverse of it, well, we can't just switch all the x's and y's because there's infinite x's and y's. But what we can do is we can take our function and we can write it in sort of standard form. We're going to replace f of x with y, and then we're going to switch them out. We're going to switch out the variables x and y and then solve the equation and rewrite it for y. And then the last thing that we'll do is we'll just replace with the inverse function notation after we've written our new equation. So what we're going to do is find the inverse of this function, then we're going to graph it, and we're going to see a special relationship with the graphs of inverse functions. So first thing that we want to do is we want to take f of x and we want to change it to a y. Rewrite this equation as y equals 6x minus 1. All that f of x is doing is telling us that, hey, yes, this is indeed a function. We know for sure that this is a function. And we're going to take x and y and we're going to switch them. I'm not moving anything else in my equation. I am just switching x and y. So instead of y equals, it becomes x equals. Instead of 6x, it becomes 6y. And then the -1 stays the same. Now our new goal is to write this in terms of y. We want to get y isolated by itself. So we use our inverse operations. Starting with addition, subtraction, we want to move that -1 over. And so x plus 1 equals 6y. And then we can get rid of our coefficient by dividing both sides by 6. And then that will leave us with y equals x plus 1 over 6. And then we just want to replace that y with the function notation, but with the inverse function notation of x, let's not forget that, x plus 1 over 6. And then if we want to write this in slope-intercept form, just to make it a little bit easier for us to graph, it's going to be, so the inverse function of x will be 1, 6x plus 1, 6. Okay, so we just take that denominator and we're writing it with both terms individually so that we have our equation in slope-intercept form. So with slope-intercept form, now we can plot that I have a y-intercept at 1/6, and so that's going to be really low, right about here. Okay, 1/6 is approximately there, and then we're going to track our slope. And so we're going to go up 1 and then right 6 places. So 1, 2, 3, 4, 5, 6. That's going to put us with something right about there. And then we're going to go down and 1, 2, 3, 4, 5, 6. So there's another point there. And what we can do now is we can go ahead and connect our line. That is a very poorly drawn line. Let me see if I can do that better. That's a little bit better, not perfect. Okay, but there's our new inverse function. We switched the x's and the y's, and now we've got our new line. Now there's something special about inverse functions, is that they're always going to have this kind of relationship where they are going to have this reflection across this imaginary line that goes through here. And this is the line y equals x. This is our most basic linear equation, y equals x. And we're always going to have this kind of mirror image that we see across this line, every single inverse function. And so when you're drawing your inverse function and you're graphing it on the coordinate plane, if you don't see this symmetry being formed, then that's a hint that either your equation is wrong or you graphed it wrong. And so you always need to be able to see that symmetry. And something that we can do to check our inverse functions is that we have this relationship with composition. Remember that this symbol means composition, not multiplication. Composition. And so whenever we compose a function into its inverse function, or vice versa, we compose the inverse function into the function. Once we're done simplifying, it always equals x. And so this is something that we do in order to prove whether or not we have a inverse function if two equations are inverses of each other. And so what we're going to do is we're going to show that these two are functions. You want to pay attention to the directions a little bit because sometimes they give a hint. Show usually means that, yeah, these are going to be inverse functions, so make sure your work matches. If it says to prove whether or not or identify whether or not it is a function, then it could be either way, and you'll just want to be careful. But we're going to do both compositions here. We're going to compose f into the inverse, and we're also going to compose the inverse into the function. So let's write this a little bit differently first. Let's write this as the inverse of f of x. And again, this just kind of reminds us that we're going to put f of x inside of our inverse function. And f of x is x to the third minus 5. So we're going to take the inverse of x to the third minus 5. We're going to take it and we're going to plug it in. Okay? Let's write that 5 a little bit neater. There we go. Okay? And so now this is our input into our inverse function. So I'm going to take this entire expression, I'm going to plug it in for x in my new equation, into my inverse function that they gave me. And so now we're going to go ahead and rewrite this as x to the third minus 5. That's that x value right here. And then the rest of the equation is going to go around it. I've got the third root and I've got plus 5. That's just this and this part getting put back in. And then from here we just want to go and simplify. Now I check to see, do I have any multiplication outside of my parentheses? No, so I can go ahead and get rid of my parentheses. And so I'm left with the third root of x to the third minus 5 plus 5. And then we're going to combine like terms. Well, if I have a negative 5 and a positive 5, those are going to cancel out, leaving me with the third root of x to the third. And then if I take the third root of x to the third, I end up with just x. So now I know that yes, okay, we're halfway there to checking to make sure that these are indeed inverse functions. Now we need to check it the other way around. Usually it works. To be honest, I don't ever think I've seen a time where it doesn't work, but you could make a mistake in your calculations, and this is going to be the second way to make sure that you get it correct, because you do need to check that both of them will simplify to be x. So we're going to rewrite our notation, but we're not doing inverse first this time. Now we're doing our function first. So f of the inverse function of x, and so that just reminds me that my inverse function becomes my input, and then we go ahead and actually replace that with the inverse function, which is the third root of x plus 5. Okay, so we have the f of the third root of x plus 5, and that's going to be our input. Let me erase some of these marks up here so I can do the same thing again. What we're going to do is this part will be the x value that I replace in my function. So I'll take the third root of x plus 5, the third root of x plus 5, third root of x plus 5, and that's my input, and then I'll build the rest of the function around it. And so I see that the x value is being raised to the third power, so I need this to be raised to the third power, and then I'm subtracting 5 from the x value as well, so we'll subtract 5. And now from there, we'll just go ahead and simplify. Well, the same thing kind of happens as before. If I have third power and third root, those are going to cancel, leaving me with x plus 5 minus 5. And then when I go to combine like terms, if I have a positive 5 and a negative 5, those cancel out to be 0, leaving me with just an x. And so by showing all of these steps, I've proven that these two functions are inverses of each other. And again, it's very important to note this says show that it is. So this is kind of the work is the answer. The work is the answer in identifying that these are inverse functions. And that's where we're going to stop today. Moving forward, when we go into exponential and logarithms, we're going to see that they are inverse functions and they have that very close relationship, and we use that in order to identify some key features as well as to graph and solve different equations because they go so close hand in hand with that.